Chapter 5, Number 7. A 0.5 kilogram object is acted on by a force whose x component varies with time, as shown in figure 526 below. Draw the corresponding ax versus time graph for this object. We will make one additional assumption, which is that this is the only force acting, at least in the x direction. If there are other forces acting, we don't know anything about them, and so then we'll be done. But if this is the only force acting in the x direction, then it is the net force acting in the x direction, and we can go back to Newton's second law and say that the sum of the forces in the x direction is the mass times the acceleration in the x direction. So here we would have the force Fx equals max, or ax equals fmx over m, which means at every point we would just divide whatever the value of the graph is by the acceleration, by the mass, the 0.5 mass, to get the acceleration. So really it means that the shape of the graph would be identical. The acceleration would do this, and do this, and then do this, and the only difference might be what is the scale of it. So on correct scales, we would end up saying that, right, now we have a correctly scaled graph, and we'd say that when f is 1, in other words, here, we would expect a to be 1 over a half, or 2. So for the first second, it does something like this. And then when f is 4 at this moment, then a should be 8. And we can see that there's a straight line between them, so every value would be, for instance, at 2.5 we'd have 5, etc. And so we get that. And then at 5 seconds we're back down to 0 force, so therefore we're at 0 acceleration. So something like that. Well, that's not so great, but better. So our acceleration graph looks like, but is a rescaled version of the force graph.